Hello, welcome to Introduction to the EM Algorithm. So in this tutorial, we're going to break down the expectation maximization algorithm, not just in theory, but a step-by-step real example with a missing data point. So you're going to see exactly how the EM algorithm helps us estimate parameters when some data points are incomplete, a situation that's very common in the real world. First, we'll walk through just one iteration of the E step and the M step so that you could see the mechanics of how the algorithm fills in missing values and updates estimates. Then in the second part, we're going to show you how the algorithm converges by tracking the log likelihood and explain what it's really optimizing. So whether you're a data scientist, a researcher, or just EM curious, you'll walk away with a clear and intuitive understanding of how the algorithm works and why it's so powerful. Here's a diagram that basically shows the outline of the algorithm. We have the expectation step, the maximization step. If it's converged, it'll stop. If it doesn't, it won't. Okay. So now moving on to just showing one iteration, I do want to make and emphasize a point that it's very important for you to understand basically how values are indexed in a matrix. Okay, so when we start off with columns, we got 0 and 1, and then 0, 1, and 2. Okay, so knowing this is actually very important in order for you to follow the logic that I'm going to be talking about right now. So let's start off basically with a matrix, and we see that we've got a missing value. Okay. So now where is this missing value located? This column is 0. This column is 1, 0, 1. So it's 1, 1. Okay, where NPNA and N is. Here we see that 0, 0 is 1. Okay. But it's important for you to know that. Okay. Now if you go 2, 1, just to check our logic again, it would be 6, right? Because here, this is the second row here, and this is the first column, right? 0, 1, 2, 0, 1. Now here, we basically are going to take a complete matrix, okay? Get a complete matrix, right? And if I run this logic here, we're going to get 1, 2, 3, 6, okay? And the reason why we would want to do this is to get estimates, right, from the complete matrix. So when we do that, we get a mean of 2 and 4. 4 divided by 2 is 2. 8 divided by 2 is 4. Okay. Now, we also need the covariance matrix, right? And we say row variance is equal to false. So we're going to say, we're going to get this, 2, 4, 4, 8. Okay. Um, remember, this is something that I've emphasized in my earlier videos, is that here the diagonals are the variances, okay? And these are the covariances. The covariances should be the same. They should be equal, the off diagonal. Okay, so I do want to emphasize that point. Um, so row variance is equal to false means each column is a variable and the row is an observation. Okay. Now we see X obs, which is 1, 0, which is 2, 2, right? Row 1, and then column 0, okay? That's observed. What's the observed in the mu? It's mu 0, which is 2, okay? Because we're taking this estimate from a completed matrix without the missing, okay? Right? So we know that the second column is missing, right here. So we take the second value, okay? So what we're looking at is basically the index value of what is missing. Even though we took the mean of a complete matrix, we still know, okay, that the second index is missing. So we say mu missing is equal to mu1, which is 4.0. And if we parse basically the covariance matrix into sigma 0, 0, which is observed, right? Variance of x1, sigma O, sigma missing is sigma 0, 1, x1, x2, sigma 1, 0, x2, x1, and then variance x2, x1, okay? This is important, this covariance, okay, between the missing and the observed, because that's something that we need um, to execute the EM algorithm logic. Okay? So now we've got this sigma OM. I mean, I just basically run it and we know it's 4, okay, as mentioned earlier. Knowing this is extremely important, like how to parse a covariance matrix, how to basically take the means of a matrix that don't have that have a missing or whatnot. So these are important logical ideas that need to be well understood in order to see the mechanics behind a EM algorithm correctly. Now, I've done the Python logic. I'm going to move on to the mathematics, and you're going to see that the mathematics and the programming are basically just the mathematics is an expression of the programming, right? The programming language. I mean, we have to, in many cases, we have to take the math and be able to program it, right? Um, that's somewhat of the challenge of implementing something from scratch because you not only have to know the programming language inside out, you have to know the mathematics inside out. So there's the a little bit of a challenge, but it's a lot more rewarding to know both because you're not going to be one of those people that have superficial understanding of what's actually going behind the algorithm. So I'm going to go through the mathematics and hopefully you'll kind of see what we did in the programming language, right? So we say that 2D random vector, x is equal to x1, x2, transpose draws from a multivariate normal distribution, okay? Mu, here's the covariance matrix, right? The mean vector is mu1, mu2. You could see that we did that. We calculated that from the complete matrix, right? And then we saw that we took the covariance matrix and we see that the diagonals, sigma 1, 1, sigma 2, 2 are the variances and sigma 2, 1 and sigma 1, 2 are the covariances, okay? So if we observe x1 is equal to x1, but x2 is missing, which we saw in our columns, right? I don't want to, we see that in x2, this column is missing, okay? We could take, um, we could get an estimate of x2, right? The missing value based on this conditional expectation. We have mu2 plus sigma 2, 1, which is a covariance, okay? Divided by sigma 1, 1, which is a variance of x1. And then we do x1 minus mu1, okay? And x1 minus mu1 is obviously the observed. Now, if we put it in a multivariate case and then basically generalize it, we could say the expected value of x missing given x observed is equal to mu m This subscript represents missing plus the covariance matrix of MO times the covariance inverse of the covariance matrix of the observed, which are the variances, which is the observed. Okay. Times XO observed minus mu observed. Okay. I'm sorry. So covariance OO here is it's the covariance, but between the observed variables. Okay. And this is the covariance between the missing and the observed. This is not the variance. So I apologize for that mistake. Now, we've got this to kind of guide us in like how we set up the variables, right? We've got mu missing plus sigma MO divided by sigma OO observed, right? Times X observed minus mu observed. And then we come up with the estimate, which is 4. Now we've come up with this estimate 4. We could plug in that missing value into the X matrix that we had, into the array. So the position is 1, 1, which it was missing, right? Because it's 0, 1 column, 0, 1, 1, 1, right here. We're going to plug that in now into the matrix, and we get a 4 here. Now we're going to move on to the M step. And remember, this is just one iteration, okay? The M step, we're going to now update the mu and the sigma from the completed data, okay? So we do MP mean of X, axis is equal to 0, which is taking the means of the columns. Okay, so if we do that, we add 1 plus 2 plus 3, which is 6. Divide that by 3, we get a 2. 2 plus 4 is 6, plus 6 is 12. Divided by 3, that's 4. Okay, so this is the updated mean from the completed data where we filled in the estimate using this expected value equation. Okay, now we take the same thing and we take the covariance. Okay, and we take the covariance of X, and then we get this of the completed matrix. We always use row variance is equal to false. Okay. And we get a 1, 2, 2, 4. Okay. 2 being the covariance matrices, 1 and 4 being the variances of their respective variables, X1 and X2. Now we're going to go on to adding the actual iterations so you maximize the log likelihood. Okay, and it's important to make the point that we're actually maximizing the log likelihood. Where in other cases in optimization problems you could be minimizing the negative log likelihood and whatnot. That's not the case here. We're going to be maximizing the log likelihood. Now, going back to our original equation, we've got the M step, E step, which I showed earlier, right? And we should know that the M subscripts are for the missings. MO is basically the missing and the observed, and the observed and the observed, right? So this matrix here, I mean, if I should have mentioned this earlier, it's basically a connection between the observed and the missing, right? This covariance matrix, okay? And this is the covariance of the observes, okay? XO observed minus mu observed. Now in the M step, we're given a multivariate Gaussian distribution with mean mu and covariance matrix, okay? And this is how you would formulate it. Basically the summation symbol of the Gaussian, the log Gaussian, okay? Where xi is the data points And mu and the covariance matrix is a probability density function of a multivariate Gaussian distribution, which looks like this. Um, D is dimensionality. Okay. This here is the determinant of the covariance matrix. And this is the Mahalanobis distance between xi and mu I, scaled by the covariance matrix. The inverse, actually. Okay. So I mean, if you were to expand this term just to one data point, which is always useful, because if you have a generalization, it's actually just a good look at it's good to look at just one example. Here it would be, right? Just xi negative d2 log 2 pi minus 1/2 log um, the determinant minus 1/2 xi minus mu transpose times the inverse of the covariance matrix times xi minus mu. So at each iteration, this will update. Okay, we don't see this sometimes in code because we've got a lot of nice, useful functions that take care of the mechanics, right? And we'll see that. I'll show it to you in the code. So I mentioned like basically that we need the determinant, but there's a potential pitfall that your matrix might not be invertible. Okay. And if you look at this example here, I give two matrices. One is invertible and it's full rank, meaning that the columns are independent. Now I give a rank deficient matrix where it's non-invertible. And it's a very exaggerated example in the sense that we see that the columns have a dependency here, right? We know that 1, 2, 3 is a multiple of 2, 4, 6. I mean, is 2, 4, 6 is a multiple of 1, 2, 3. 369 is a multiple of 1, 2, 3. So there's a clear dependent structure, and this is rank deficient. The reason why I bring this up is because when you run an EM algorithm on data, basically that has a lot of missing data or you've got a lot of columns, these issues can occur. Okay, so if there's an error that pops out where your algorithm can't run, you're going to be able to debug it by seeing that there is a dependence type of structure. You're going to be able to pinpoint the issue. Okay. In the example that I give, we're gonna basically regularize it where we perturb the values, say maybe to something like this, that will make it not dependent. Okay, but I'll show you when I get there. For now, let's go on to kind of looking at the matrix that we're going to run. And I'm going to go over this again just to reiterate some points and then introduce something um, new. Okay. So, I mean, we know that we have this matrix here. Okay. And we've got the missing here, right? We know from the index values that it's 0, 1, 2, 1, right? So the row is 1, 2. Is the exact missing. Here I just go 1. Okay, so this is new here. So let me just, here it's 1 and then to 2. 20, negative 5. Okay. So we're taking row 1 and then 0, 1. Okay, this 2 is not, we're not taking 2, we're taking the ones that are observed. Okay. Then we take the index of where it's missing. You see it's array 1, MP where, MP is NANX, right? And then we get the index, which is array 1 and array 2, okay? Which is 0, which is row 1, column 2. Okay, so that's what that means. Now we take the index and we plug in the column means, okay? I didn't actually do the column means here. But what I'm trying to get at here is like we have some calculation of the column means, and then we replace it, okay, with 4.667. We saw that earlier. I didn't do it here, but we've done it. We get this something called column means where we take each of the column values, right, and then we replace it, okay, on the completed matrix. And then we also do that for the covariance matrix, right? We take the covariance matrix of that completed data set, we get something like this. Now, in order to get the sigma observed, we do 2, 2. Because we know that this up to this here is observed, right? 0, 1, 0, 1, 2, 3. 0, I'm sorry, 0, 1, 2, 3. That's exactly right, right? That's observed. Okay. Excluding this index. Okay. So if we do sigma 2, 2, we know that we get something like this. Okay, we get this part of the matrix. Okay. And if we do sigma 2, 2, we get this part of the matrix. Okay. Now, it's important to know before I should have actually said, talked about this a little bit earlier. We get this complete matrix, okay? And one second. So what I wanted to actually say was basically that if you see this sigma MO, let's take the sigma MO, which is missing and observed, right? The covariance, okay? We get sigma 2, and then this colon 2 is 1 and 2, right? Basically, what we're looking for is if we were to look at the original X matrix, we see that this is 2, where the missing is. We want to have this relationship between the columns that are not missing, okay? So that's what that means. Okay, hopefully that clarifies um, the 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 point I was making earlier. Now we also have something where we're tracking the log likelihood, and basically we're going to use this negative NP-inf. Okay, and I mean I just put this example here because I want to show that like after each iteration we're going to be tracking it. We need to initialize, okay, like a loop. For those that are familiar with for loops and initializing variables in optimizations and whatnot, but that's what we're going to have to do. And this will basically track it, okay? This LL change. So these are some of the major ideas um, that you're going to have to know in order to understand now the full completed idea of the EM algorithm. So let's go through this. Now we've got this data set. Moderate variance, right? If there's too much variance in the data set, another point to make is that it will probably not converge as quickly. So that's another thing to keep in mind. Okay, so that's important to know. Now we do the initial imputation, which I showed you, right, where we fill in the values, okay, where we take the column means and whatnot, and then we fill it in to the matrix, right? Then we take the initial mean and the covariance matrix, which we did. Now here we go through like some initial values, right? We have to initialize the run, okay, which I call it initializing the run. People call it, I think the same thing, to be honest. So here we've got max iterations, 100, the tolerance level, the previous likelihood, which we set at negative NP-inf, right? The regularization value. Remember when I said that there might be dependent columns? We need to like change that a little bit, okay? So that we don't have this program stop, okay? Based on based on that condition that I talked about earlier, right, with the determinants. Now we store the log likelihoods, and the reason why I do that is because I want to track the change and then actually show the graph. So here we're regularizing the covariance matrix, okay? MPI is a identity matrix, and we take that regularization value, we multiply it by that, and then we add it to the covariance matrix, okay? Now I showed you all of this here. This is the E step. We regularize the covariance matrix. We take the inverse, and then we apply that expected value equation, okay? These are dot products. Then we impute that value, that missing value into the matrix, okay? That missing value that we saw earlier, 1, 2, 0, 1, 2. So it's important, like I was mentioning, and I want to reiterate, to know these index values inside out so that in an example like this, you could pretty much quickly do it automatically and you could worry more about concepts. That's kind of the, um, I guess, the major hurdle in learning statistical ideas and then being able to program it, right? Because you have to know the mathematics and the programming. And here's the M step. So we take the sigma, we take the covariance matrix, we regularize the matrix again, and the log likelihood. So remember when I mentioned that xi, here, this thing, that's what we're basically doing, right? When we do a loop for the likelihood, okay? We take this NP sum because we're taking the log likelihood, right? Multivariate normal log PDF, which we get from SkyPy, x mu, mean equals mu, covariance equals sigma for x in x. So this is the little xi, okay? That's how you would translate it. Now we append, after each log likelihood run, we append it to that list. And then we track the change, okay? And then I print out basically a bunch of iterations. We impute it each time, the x12, the log likelihood, the mean vector, and the variances, okay? We track the changes, okay? And then it converges when it's less than the tolerance, okay? So this should look familiar to those that know the idea of optimization and have looked at things like gradient descent and whatnot, right? I mean, it's similar ideas, a little bit different, obviously, but it's similar ideas, okay? The idea of convergence and whatnot, right? To stable parameters, okay? Um, Now we print them out, the final mean vector, the final covariance matrix, and then finally the imputed uh, data matrix, and then we plot the log likelihood convergence, okay? And if we look at it, basically after each iteration, we could see the changes, okay? The delta becomes a lot smaller, right? And we see that this value here is changing. Okay, these two, the first two are remaining the same, obviously, because they're observed, and these are the ones that are changing, the third, right? And then we also see the log likelihood delta, the log likelihood increasing, and the delta becoming smaller. And we go down, and it converges at 50. Okay, and then we get the final mean vector, the final covariance matrix, and the imputed matrix. Okay. Now, I mean, looking at this, it's going to be somewhat, taxing, especially for somebody, especially if you're going to show it to somebody that might not know a lot about, the mathematics or the mechanics behind something like this. So we could just show a graph, right? It converged, and you could explain it in a very simple way in the sense that, the parameter estimates are stable. And this is the best thing that we could get, okay, based on using this technique, right? We've taken care of the missing values. by using this EM algorithm technique. So that's it for now. I hope you learned something. I hope in the future to actually talk more about some variations of the EM algorithm. I discussed the Gaussian mixture, which scikit-learn takes care of beautifully, but I'd also like to talk about it from a technical point of view, like similar to what I've done today in this session. So thank you very much. If you enjoyed this video, please hit like or subscribe. Take care, and I hope to see you soon.